Hello, welcome to Aerospace and Mechanical Lab 2. Today we are going to talk about beam vibration. So we will talk about the theory behind vibration of a beam. We will talk about different types of beams, support systems for a beam, specifically free beam and cantilever beam. And we will talk about vibration damping. And eventually we will talk about the vibration test uh, as it is in the labs. Okay, vibration. Vibration is essentially just a mechanical phenomenon in which oscillation occurs. So a system like this, when you leave it, this mass is going to force a spring to vibrate back and forth. We have different types of vibrations. The first one is a free vibration. It happens when a mechanical system is set in motion with an initial input. So essentially, the idea here is that you create an initial disturbance and remove that disturbance. Doesn't stay. Can be any type of disturbance. Force vibration, on the other hand, is where your disturbance stays. You can apply either a time varying or constant disturbance to your mechanical system. And if it stays there, you are going to have a force vibrating system. We have different types of inputs. We can have periodic, a steady state, and a transient input, or just a random one. All of these can cause vibration in a mechanical system. And your vibration can be damped when the energy of the vibrating system goes to zero. Like in a scenario like this, you will see a vibration energy dissipation, vibration energy loss due to the presence of air friction, essentially, with the friction with air. And after some point, it just stop vibrating, and all of its vibration energy is going to be lost. So this is where we say the vibration is damp. How long does any system takes? How long does it take any system's vibration to dampen out is an important parameter for us, and in vibration generally damping ratio. This is a part of this lab as well. So we can simplify vibrating system by just using a system of mass, a spring, and damper. You have a vibrating mass, you have a spring constant, and a damping system. Again, this can be any vibrating system. We can replace any vibrating system by a system of a spring mass damper. That's what it's called. So the type of forces we have here is the vibrating force that can be time varying. We have the inertial force of the mass. We have the elastic force of the spring, and we have the damping force of the damper. The equation of motion for this type of system is going to be like this. We have mass multiplied by acceleration, which is location double dot, plus the damping constant multiplied by your velocity, which is a location dot again, plus the spring constant multiplied by the location at any time. Can be equal to system. So this is a system um, in which we can analyze the vibration, the frequency, the location, and different sorts of things. If you don't have a damper in your system, then your vibration equation of motion simplifies to something like this. And the general solution for these type of systems is gonna look like this. You don't really need to know partial differential equations for this course, but the thing is, this is a differential equation, which general solution looks something like this. So the location equation of motion, general solution to the equation of motion for any vibrating system is going to look like this. It's a sine and cosine function, sometimes a hyperbolic sine and a hyperbolic cosine function. Whenever you see an equation like this is telling you, this is giving you the equation of motion for vibration. And we define this parameter, square root of spring constant divided by mass, as the natural frequency of a system, omega of n. So the idea is, if the frequency of the disturbance is this much, is equal to the natural frequency of your vibrating system, the vibration is going to resonate. So you're going to see essentially the vibration with the same frequency in the beam, or an increasing frequency even, in your vibrating system. Okay, so if we graph the location with respect to time, we are going to see a graph like this. So this is the location of this mass at different times. As you can see, this is moving back and forth, and as you see, these sinusoidal functions, which is something we could have guessed based on the fact that the general solution for this is a sine and cosine function in general. Okay. In our scenario, we are dealing with two different types of beams. It is one setup essentially, but your job as the student is to have different perspective when it comes to the beam. One perspective is free beam. What is a free beam? Free beam is a beam which has no support on both sides. This is going to be your beam, and all the information of the beam is given right here, right? We are going to apply a load here in the middle, and it will start vibrating. There are no supports, there are no fixed support, there are no moment support, there's nothing, right? It can move freely. That's the idea. But this is a theory of it. In reality, we are holding the beam in the middle, right? So the reality does not resemble this free beam vibration exactly. That's why we have the second perspective as well, to compare which one of the perspectives, theoretical perspective, resemble reality more. Let's look at a video with a free beam vibration to get a better understanding of what it is. We're going to talk about the vibration problems in the next slides. We have a system, our beam is much smaller, and we apply load at only one location. But the idea here is that we are holding our beam at one point, and these two ends are just free to rotate, to vibrate. I'm sorry, as they want. Increase the frequency of the vibration, the bending mode, the vibration mode is going to change. We're going to talk about that in the next slide. Okay, so we did talk about the natural frequency. Natural frequency, we have different natural frequencies for each beam. That hence omega of n, as you can see here. Natural frequency is not just one value. Essentially, we have different modes of natural frequency, which is going to result in different modes of vibration. For the first mode of vibration is the first natural frequency of the beam, right? And for a free beam, first mode of vibration is going to look like this. So it will vibrate like this. This is the location, a snap of a location of a beam during a free beam vibration. But what does this graph tell us? So on the vertical side, we have the normalized displacement, which essentially means that we have divided our amplitude at displacement, vertical displacement of the beam. We're talking about vertical displacement of the beam, right? Not the location. We have divided it by the amplitude of the frequency, essentially maximum displacement. That's why you see the maximum of 1 here. In the middle, we have a value for 0, means that there is no vertical displacement. That's value of 0. And here, we don't have time anymore. We have the normalized location, so x divided by L, essentially where you are standing on your beam. That's the idea. Normalized, that's why it goes from 0 to 1. So first mode of vibration, what are we going to see? We're going to see the maximum vibration at the two ends of the beam, and then some point in the middle for mode 1, we're going to see no displacement at all whatsoever. See, it does cross 0, which means that there is no vertical displacement. There is no vibration at these 2 points. These 2 points are called nodes. Let's go back to the video. See, first bending mode looks like this. So at these locations, we have nodes where the vertical displacement or vibration is 0. See, they are using sand here, and the sand is going to a location where the displacement is 0. So this location is the location of the node, and we do have another one for the first one. As you increase the frequency, you enter the second mode of vibration. The second mode of vibration for a free beam, we are going to have 3 nodes where there are 3 nodes which vibration is 0. You see, sand is going to gather at 3 different locations. See, 3 nodes. Beam is going to act like this. At locations where vibration is 0, it is going to vibrate. Really simple. So the idea is, if you increase the mode of vibration, if you go to the second mode of vibration for a free beam, you are going to pass 0 3 times, meaning that you will have 3 nodes. And if you increase it even further, you are going to enter the third mode of vibration, in which you have 4 nodes. 1, 2, 3, 4. So your job in the lab is essentially to increase the frequency that is applied to a beam, to your beam, and find the location, the experimental locations of these nodes for each mode of vibration. And then you compare these values to analytical values. Whichever is closer is going to be the correct perspective. If you recall, I talked about 2 different perspectives we have. The first one is the free beam perspective. Okay, so how do we calculate the natural frequency though? The natural frequency is calculated using, for our specific beam, is calculated using this formula. We have the modulus of elasticity, we have the moment of inertia, or the second moment of area, we have the area of the beam, cross-sectional area of the beam, we have the density of the beam, we have the length of the beam, and a vibration coefficient. This is essentially a coefficient that changes at different modes of vibration. Okay, and the general equation for the vertical displacement, see, this is x of n, normal or vertical displacement normal to the beam. So this is essentially the amplitude of your vibration, is a function of the location on the beam and all of these other parameters. Again, the idea is at node positions, this normalized value is going to be 0. Okay, so for our beam, you actually have to use a software. It can be Excel, Python, MATLAB, whatever software you use. You can use online libraries to find the nodal positions for our beam, for a case of free beam with this equation. I'm going to upload another video in which I'm going to show you how to actually do these calculations in Excel or Python. But the idea is you have to do the calculations yourself. And we do know everything here. We know the length, we are going to know beta. We're going to give you the values for beta. And for your case, it's just apply and chart in the solution to a sine function. The other next perspective we are going to follow is the cantilever beam vibration. So essentially, as I said, let's go back to the original beam. In our original beam, for the free beam perspective, free beam perspective, we are holding this in the middle and vibrating it, right? We are going to use the same beam and same setup for the second perspective, but we are going to treat this as two different beams. So this hole in the middle is going to act like a fixed support. Is this a real fixed support? No, because it is moving, it is vibrating, but this is the assumption we are making. We want to know which one of these assumptions, support assumption about the supports, resembles the experiment better, right? Okay, so fixed end cantilever, essentially we are holding our thing in the middle. We are going to have vibration on two sides. That's the idea. And the modes of vibration for this is going to look like this. The first mode of vibration with the first natural frequency, again, we are going to talk about how to do the calculations for that, is going to look like this. There are no nodes here. The fixed support is not a node. This is a support, right? There are no nodes here. So the first mode of vibration for the cantilever beam has no nodes. Second mode of vibration is going to have one node, and the third mode of vibration is going to have two nodes. So the number of vibration is essentially n minus 1. The other one was n plus 1. Okay? And the natural frequency of the beam is calculated like this with a slightly different formula. And we already know about this. The general formula for the normal displacement or the amplitude of vibrations is calculated by this. Again, you have to use a software, or you can look up Google or whatever to find the values. We are looking for the node values. This gives us the node value. So if you set this equation equal to 0, you are going to find the node values, essentially the location at which nodes happen. Like in this case, we have the location. Let's say this is 1 meter. The location x is of the node, where x of n is 0. X is going to be, let's say, 90 centimeters and 50 centimeters, for example. So you calculate this using this equation, and you compare the values to the experimental values that you have gathered from the experiment for these exact points. Whichever values, whichever comparison between the free experimental calculations and the theoretical calculations, and the comparison between the cantilever experimental calculations and the theoretical calculation. Whichever gives you a lower level of uncertainty, you can accept that lower level of uncertainty, lower level of error as the theory that can resemble your experiments. And this is the equation. And then again, we are going to give you the beta values for all of these in a table that is at the end of this lecture, and I'll make sure that it is also in the lab instructions. But the rest of the calculations should be done by you. We are also going to give you the frequencies, the natural frequencies. Okay, the third part of the experiment is damping calculations. Again, the idea is when you remove the external load, the vibration is going to dampen, is going to die. And the speed at which that happens is important to us. See, a damped vibration. Okay. We are looking for these type of graphs. So essentially, we have a couple of strain gauges installed on our beams. And when you start vibrating the beam, the strain gauge is going to record a strain value, right? Meaning that higher the vibration, higher the strain, right? And your vibration dies, you are going to see a lower and lower value of a strain. This is a damping vibration. We can use this data, the strain data, to do damping ratio calculations. So essentially, this is going to be your first amplitude, initial amplitude. This is going to be amplitude after a number of cycles, n number of cycles. So essentially, you export this type of graph from your LabVIEW software, and then you do this type of calculations. Right? You take these two amplitudes, you count the number of cycles you are using, calculate the logarithmic decrement, and then using that calculate the damping ratio. Okay, So 3 parts of the experiments. We did talk about vibration, damping, free beam, cantilever beam, and so on and so forth. Let's talk about the lab itself. The lab is going to look something like this. You do need a computer to read data off of a strain gauge that is either installed here or installed at the end of the beam. We have a shaker, which is holding the beam in the middle. It's connected to an amplifier, a signal express system. So this part, I have simplified this semester. You're going to see a different signal generator. It's a very simple, just read the frequencies and add the frequencies if you want to make things simpler for you guys and a little more reliable. And you treat this as a free beam. You give the signal generator, using the signal generator, you are going to give this beam the natural frequency, first, second, and third natural frequency of a free beam, and record the node locations using a ruler and your pen. And then you treat this as a cantilever beam. So you start from the middle, you record the node locations for the natural frequencies of the cantilever beam, which are going to be different. And then you compare them to the theoretical values. Okay, so I've given you the beta values for the free beams right here. We are going to go up to the third mode of vibration. So beta 3L. And then if you want to go even higher, this is the formula you have to use for your beta multiplied by L. And for the cantilever beam, values for beta are like this. You're also given the frequencies at which the natural frequency is essentially frequencies that are natural frequency of the beam. So you just have to use these to record your experimental data and use this to solve that huge equation using Excel or MATLAB or whatever you want to use. Okay. This says 5 here, but it should say 3. I will make sure that it is correct on the uploaded lecture notes. And that is it. Please let me know if you have a question. Please make sure to watch the video that I'm going to upload right there on how to actually do the vibration lab and how to record the data. And also, I am going to upload another video in which I'm going to show you how to do the calculations in Excel or MATLAB or Python. I will upload multiple videos using different softwares. Please let me know or let your TA know if you have any questions or concerns, and enjoy the rest of your day.